Hey there, ladies and gentlemen. Welcome back to part 2 of making that amide. I left you on the last video with this question. Give me a mechanism for this transformation using base, water, and heat. And what you get out of it is the carboxylate salt and ammonia, where this nitrogen here is the same as that nitrogen there. Hopefully I really didn't need to show that to you because there's only one source of oxygen, one source of nitrogen in the whole thing. But you know, I like to be thorough. So we start with this, our amide. And if you thought the first step was the base attacking the carbonyl carbon, you would be exactly right. One thing I hope none of you did was try to protonate anything, because we're doing this in a basic environment and protons don't freely exist in a basic environment. They're tied up in covalent bonds. This is reversible to where you're here, here, and NH2. Odds are extremely high that 99.99% of this reaction is going to push back towards the product. But for the very small amount that will go forward, here's what it looks like. Reform the carbon-oxygen pi bond, knock off the nitrogen, and you result here. A carboxylic acid and the NH2 amide ion, which is really a hot anion. So it rips the proton off the acid, and what you wind up with is the carboxylate salt and ammonia. Now, if this were a, let's say, this was your amide with hydroxide, water, and base, this would be the product you get. The salt and the amine. All right. Hopefully you got that, and hopefully you understand. If you didn't, hopefully you understand where you went wrong. You know, what bad choices led you to this stage of your life. Don't dwell on it too long, because it makes me depressed just thinking about it. All right, those are really two of the only reactions we have in terms of amides going back and forth to the rest of the acid derivatives. What I want to talk about now are a couple of non-standard reactions. So let's say we have this amide, and we react this with one equivalent of lithium aluminum hydride and another equivalent of water. Secondly, because you don't want to have it tear your face off, this is what you get. The amide oxygen is removed completely. Now, this is another example of a reductive amination. Mechanistically, this one is a little wonky, but let's work our way through it. So, we've got this as our amide. Here's our reducing agent. Nucleophilically attacks the carbonyl carbon, opens up the carbon-oxygen pi bond. This is not a reversible step, which puts you here. And that ox anion is actually going to form a covalent bond onto the aluminum. Oh, I forgot the nitrogen half of this. No, Kurt, that's not important at all. So we're here. And what may not be readily obvious to you is the fact that this has become a decent leaving group. So that is exactly what happens when this nitrogen pushes down its pair of electrons and knocks that off, which results in this. And then another molecule of lithium aluminum hydride will attack that imine carbon now and break open the carbon-nitrogen pi bond, and what you wind up with is the amine. All right. So after this is where some of the weirdness comes in, because I want to show you this reaction, which is amide to nitrile. So the question is, how do we go from here? And it's important this will only work with the primary amide for reasons you'll see when we get through the mechanism. This amide reacting to give you this nitrile. And what we use to pull this off is our old friend Bubble Vicious. Thionyl chloride is what we use to get this reaction to go. Now, because I don't have a very fine stylus, I'm going to click over to the next page and show you this mechanism. It's actually really cool, but maybe I'm just a different breed of cat. To start with, what we've got is this amide. And remember, and part of the key to understanding how this mechanism works is amides exist in this resonance. Like so. Which makes the oxygen there particularly nucleophilic. And in fact, it's this oxanion that will attack the sulfur and knock a chlorine off. So now you're here. All right. Chlorine anion is going to pull off one of the protons, which puts you here. And believe it or not, we are almost done here, because we already have a double bond on our nitrogen. All we need to do now is find a way to get a triple bond. And yea, verily, this is what it is. Form a triple bond between the nitrogen and the carbon using the nitrogen's pair of electrons, which is going to knock off the oxygen-sulfur bond. Sorry, I didn't quite erase that right. There we go. I just wanted to show that arrow a little bit better. Knock off the oxygen-sulfur bond and then kick off the chlorine, which puts you here. And then the chloride anion will pull the proton off of that, and you wind up, well, here. Now, there are several ways you can do this reaction. Thionyl chloride is only one of the reagents. You can also use, so if we're looking at this reaction now, we could use thionyl chloride. We just went through that. You could also use phosphorus pentoxide or phosphonium chloride. All three of these mechanisms work almost identically. It's just, when I've seen people have to do this, they go to thionyl chloride. P2O5 will kill you deader than you can possibly imagine, and phosphonium chloride will do roughly the same thing. So, thionyl chloride, as hilarious as this is going to sound, is the safer of your options. And that brings us to an end of this part of the amide chapter. The next video will cover reactions of nitriles and the salt. So until then, don't forget you have a quiz you should be working on. It's currently Wednesday, April 8th. That is due on Friday, and I hope you all have a good day and a good evening.